Hello, welcome to Zoning and Controls for Different Environments. My name is Derek Smith, and I am the Terminal Unit Underfloor Product Manager. I will also be joined by Matthew McLaurin, who is the Chill Beam Critical Environment Product Manager. When it comes to zoning, you first have to understand the type of system that you're using. The system in particular that we focus on here at Titus is a central plant air conditioning system. When dealing with a central plant air conditioning system, you are delivering a certain amount of air to a particular building. But how do you go about breaking down that air into zones in order to ensure thermal comfort for the occupants? But one way of achieving this is by using terminal units. Terminal units are a key component in a central plant air conditioning system that provides overhead air distribution. One of the good things about terminal units is with the incorporation of various types of controls, you can get very efficient and accurate control to help you manage the efficiency of your air distribution system. Another thing that's important is unit placement. So you have to understand the different loads challenges your building has. This will help you in correctly placing and sizing your terminal unit to fit your particular application. When it comes to VAV unit application, it's also important to know which particular VAV unit to apply to your particular application. One of the easy ways to zone a building is the use of thermostats. You use the terminal units to deliver air to a particular space in the building, but thermostats give you that control that helps localize the comfort of the occupants. VAV boxes efficiently distribute airflow, and the airflow is determined by how much air is needed to satisfy the room temperature. Zoning for comfort can be a challenge in places where you have too large zones or your zone is too large to be controlled by one particular device. Terminal units allow you to break down different zones into smaller areas. That way, you won't have uneven heating and cooling throughout your space. When it's time for you to zone your building, it's important to understand how different zones affect the comfort in your building. There are two main zones when you're dealing with zoning a building. One of the primary zones is the perimeter zone. Perimeter zones require special consideration for heating and cooling loads. This is due to the fact that they are around the outside or outer edge of the building. So they are affected largely by environmental loads, which can be very extreme depending on your location in the country. Typically, a perimeter zone is within 15 feet of the external walls. These particular zones are harder to control because you do have load changes that happen throughout the day, depending on the typical exposure of your particular building. Another factor that affects perimeter zones is because you're working with a central plant air conditioning system, the further extremities of the building, which is where your perimeter zone typically is, they're harder to control because you have low pressure areas, or the air tends to drop off at a certain point the further you get away from the central system. One way to remedy this is by the use of fan-powered boxes. Fan-powered boxes have, of course, fans which can deliver more airflow in a particular zone that may suffer because the airflow begins to decline in that particular perimeter area. Also, single duct boxes with reheat can be used. When you're in a perimeter zone, if you're in a cold environment, you don't have the sufficient heat to overcome the load just by using a regular VAV box. So electric heat or hot water heat is added to a particular zone in order for you to be able to control or provide adequate comfort in that particular zone. Now for interior zones, it's a little more simple. Interior zones tend to be more thermally isolated. They're not affected as much by loads outside of the building or along the perimeter of the building. Interior zones tend to be beyond 15 feet of the exterior walls, or rather the envelope. Because they're more thermally isolated, they're easier to control. So when you're dealing with interior zones, single duct boxes are typically the terminal unit that you want to apply in that situation. They don't require reheat in these instances. Another way to zone a small section and break it down into even smaller zones is by the use of zoning with VAV diffusers. VAV diffusers are low pressure devices that allow for individual comfort or better thermal control in a space. The great thing about VAV diffusers is there is no extra ductwork that you have to apply in order to get these units in place so they can work for your particular application. They do provide heating and cooling as well, and also with the use of a thermostat, it will give that particular individual that is in that occupied zone control over their own comfort, which is always a plus. When it comes to underfloor air distribution, it's important to understand how this particular system works and all of the different pitfalls and things that you need to understand when it comes to applying this particular type of system. Typically with underfloor, with an office space, the churn rate, or how often layouts for occupants change, is a concern when it comes to providing occupant comfort. Typical overhead systems are fixed, and retrofitting them, especially to accommodate drastic layout changes, can be very costly. Underfloor systems have the advantage of easily changing the layout. With an open plenum design, reconfiguration of office layouts is simple. But if zone control is desired, the plenum can be partitioned into smaller zones. Although underfloor air distribution offers some great design advantages, with those advantages come certain design concerns. One of those design concerns is thermal decay. As conditioned air travels across the building slab, it picks up heat that has been transferred to the slab from the return air passing below it. Supply air velocities in an open floor plenum are very low, usually less than 100 feet per minute, resulting in substantial residence periods within the plenum. This residence time increases the heat transfer effect from the slab, resulting in supply air temperature rises of 1 degree to 2 degrees Fahrenheit per every 15 feet of distance from the supply point in the floor plenum. Thus, the supply air temperature may rise as much as 5 to 6 degrees as it travels a 40-foot distance from its injection point to outlets along the perimeter wall, resulting in very high cooling airflow requirements in perimeter areas. Every building will differ according to its construction, orientation, and operation, so prediction of heat transfer effect is virtually impossible. This particular term is called thermal decay. Thermal decay is the temperature difference between entering air and leaving air. The supply air is vulnerable to various building loads. Driven by heat transfer through the concrete slab or raised floor, it is easy to see a difference between zones in a particular underfloor plenum. This is decreased by increasing the supply air temperature. But how do you control this thermal decay? Where thermal decay is reduced by an increased supply air temperature. The concern now becomes the potential for higher moisture content in the supply air. The supply system must reduce relative humidity to less than 60% to meet IAQ concerns, indoor air quality concerns, and this requires dew points of less than 65 degrees Fahrenheit. Potential solutions are either reheat or blending of air to achieve a 65 degree supply, 55 degree dew point condition. System designs utilizing condenser water reheat, runaround coil face and bypass, and other strategies can be employed to solve this potential design problem. Other options include the use of separate system to dry out air or the use of desiccant dehumidification. Another way to help solve the problem of thermal decay is by the use of sensible cooling at the perimeter. Sensible cooling at the perimeter is a great complement to the perimeter cooling of an underfloor system. The perimeter zone contributes to the thermal decay, being that it's located on the outer extremities of the building and at the same time is affected by loads that are outside of the building. Sensible cooling helps to provide a thermal barrier. Passive beams should be used at low velocity with natural buoyancy, which minimizes disturbance between the perimeter zone and the mixed zone. It also allows for a reduction in air handler size because you're only treating the interior zone at that time. This slide illustrates the use of a chill beam or passive beam above the window to treat the building skin cooling loads. The building is placed parallel and adjacent to the perimeter window wall. Warm air from the glazing rises and is captured in the beam's enclosure, where heat is removed and the cool air drops back into the space. The temperature of the air entering the coil is typically about 80 to 85 degrees Fahrenheit, which enhances the beam's heat removal capabilities by 40 to 50% over what it would be with 75 degree entering air. Passive beams used in this application may provide as much as 550 BTUs per hour of sensible cooling. Ventilation and latent cooling is accomplished by manually or automatically controlled floor diffusers within the perimeter space. Although the air supplied by these outlets will still provide a contribution to the space sensible cooling, the outlet supply temperature is no longer of great importance as the beam provides most of the space sensible cooling. Fin tube heating coils installed in a trough below the access floor provide space heating when required. A narrow bar T grill extends around the entire perimeter. The coils are usually installed intermittently, leaving inactive sections where room air can fall into the trough and supply the coils. And next, we will have Matthew McLaurin with chill beam zoning.
Thank you, Derek. As he mentioned, my name is Matthew McLaurin. I am the product manager here at Titus for chill beam and critical environment products, and we're going to take a closer look at zoning for chill beams. When it comes to zoning for chill beams, it's going to be a very similar approach to that of all air systems. However, you're going to replace your single VAV terminal that's supplying the diffusers in that zone with a chill water valve that's supplying the chill beams in that zone. And that's going to control the water flow rate to the beams, where in an all air system, the VAV terminal is going to be controlling the supply airflow rate to the zone. When you look at a building overall between a chill beam system and an all air system, you're going to have a similar number of thermostats and a similar number of control loops. And really most times in a well-designed chill beam system, because of some of the inherent benefits, you're going to typically have a lower number of thermostats, a lower number of control loops, and a lower number of zones. So when we look at the two types of chill beam piping systems that are going to help set up your zones, you have your two pipe system. So this is going to be for interior zones or perimeter applications that have a separate system for addressing the heating load. The other type of system is a four pipe system where you have one control valve controlling the chill water supply to the beam, the other control valves controlling the hot water supply to the beam. This is primarily for use in perimeter applications where a building has a simultaneous need for heating and cooling throughout the day, or in buildings with long shoulder seasons where throughout the day you may have a need for heating in the morning and cooling in the afternoon. When it comes to zoning, chill beams offer some pretty big advantages over all air systems. The inherent benefits of a chill beam system, which minimize system airflow, allow for more diffusers to be installed or included in a zone. With all air systems, the ductwork very quickly becomes too large and boxes become too loud to have a single perimeter exposure tied into a single thermostat or control valve. This also lends itself to large open office plans where you can have a single thermostat controlling the water valve for all of the beams in this single large space. Here you see the diagram of a six-way valve, and a six-way valve is a single valve body that takes a four-pipe system coming into the valve and turns it into a two-pipe system coming out of the valve. So this allows for a lot of flexibility in supplying heating and cooling to the space. It also helps to reduce total installed cost of a project because now you have a single control point, a single valve and actuator that's controlling both hot water and chilled water to the space. And then you can also have this installed close to a mechanical room for ease of access and maintenance, run four-pipe system up to that valve, and then a two-pipe system out to the beams themselves, reducing the total copper or piping running out to the beams. Some of the challenges with chill beams that have prevented their widespread use thus far in North America are two main things: installed cost and concerns over condensation. And these concerns are almost always linked to one of each other. So any condensation prevention strategy is going to need at least two components. The first of which is a condensate sensor, so a moisture or condensation switch, a dew point sensor, or a door or window switch. The other half of that is a control device, so whether that be a water valve that shuts off control to the system, or a mixing valve and a pump. So imagine if we go back and think about that building with the long perimeter exposure, and imagine if you had concerns over infiltration and therefore condensation in each one of those beams. If you went in and had a control valve and a sensor for each one of those beams to shut down each one individually, that's going to add a substantial amount of cost to the project. So let's look at a real specific example from a recent project. Here's the school layout. In this layout, we're looking at a hallway or a wing on this specific building, and each room has 4 chill beams per room. So if we look a little bit closer at the piping detail for each chill beam on this project, initially there's a strainer and a valve on both the hot water and chill water supplied for each beam. Now, when you think about it, each beam also had a condensate sensor tied into the chill water supply to shut down that valve in the event of condensation. If you look at this layout a little bit closer, you see that all 4 beams are installed in the room. And if you're going to have condensation occurring on any one of those beams, you're going to have it occurring on all the beams in that room itself. And so because of that, you can go in and replace that condensate sensor on each beam and have a single dew point sensor in the space. So that allows your revised piping layout to look something like this, where now you have an isolation valve and a balancing valve on each beam, and you've eliminated the two-way valve from the chill water supply and the three-way valve from the hot water supply for each beam, and only have one serving each space. That's a reduction of 6 control valves and 6 actuators per room, and you're also eliminating 4 condensate sensors per room and replacing it with a single dew point sensor. So if we go and take a look at the room layout, what that allows us to do even further as a cost reduction is to look at potentially eliminating the dew point sensor per individual room. So you can see all 4 of these classrooms are on the same exposure. They're going to have the same solar load effectively at the same time. They're going to have kids coming out in and out of the classrooms at the same time. So you could effectively link the dew point sensor mounted in a common return for these rooms to the chill water valve for all of the beams. And so you're going to reduce your control points there. However, since you may have kids coming in and out of the classroom at different times, going to and from recess at different times, in this case, it's probably best to have a dew point sensor per room. Now we'll take a look at how you control temperature within the zone. Most chill beam systems are going to be constant airflow, so constant volume systems. So that primary air is going to be providing a little bit of the cooling, both the little bit of the sensible and all of the latent cooling to the space. And so as the room moves out of the dead band of the thermostat, the temperature, as it calls for heating or it calls for cooling, the thermostat's going to send a signal to the control valve to modulate open or close until the set point's met and you're controlling space temperature. Pretty straightforward. Chill beam systems can also have variable airflow. In these cases, the primary method of space temperature control is still going to be the zone thermostat regulating the water flow to the beams from the chill water or hot water supply load. If the space cooling demand drops below what's necessary just from the primary air cooling rate, that primary air volume can be varied so we're not having overcooling in the space. This should be only an issue in spaces that have very, very low space cooling demands, because the chill beam is going to provide about 65 to 70% of its cooling through the water coil within the beam. However, we want to be careful when applying variable air volume systems to chill beams, because all of the latent cooling to the space is being provided by the primary air. We want to make sure that we don't reduce that airflow below what's required for 2 things. One, the minimum ventilation air, and second is the minimum volume of air to maintain dew point temperatures below the supply water temperature to the space. In addition to a variable air volume approach, you could also apply a demand control ventilation approach. And so these sort of spaces are going to be those that are going to have pretty wide swings in occupancy. So conference rooms, break rooms, spaces of that nature. In these applications, a complementary pressure-independent air valve can be controlled by a CO2 sensor, and that's going to introduce additional primary air to the space as that CO2 level rises above the regulated value. Although the beam's primary airflow rate may vary as the damper opens, the CO2 sensor should adjust the primary space airflow rate according to the volume of CO2 that's sensing in the space. In this application, the beams are designed to deliver the design cooling capacity of the space at a primary airflow rate that coincides with the average occupancy of the room. During unoccupied periods, the CO2 sensor will shut off the supplementary air valve. It may also even reduce the primary airflow to the beam as well. Now we'll touch base on a couple of different condensation control strategies And there's two basic approaches. The reactive strategy, which we'll address first, and then the secondary will be a proactive strategy that's a little bit more common. So looking at the reactive control strategies you see here, so this involves the use of a window switch or a door sensor when operable doors and windows are in the space, and also with a moisture sensor that's installed on the chill water supply line of the beam itself. And so if any case moisture is detected through that sensor, the condensation contact closes, the zone valve shuts down, chill water flow to the unit suspended until moisture is no longer detected there. And the same thing happens with the window or door switch. When the window or door opens, you're going to shut down the chill water valve so that you don't have the possibility of forming condensation on the beam. The second reactive control strategy involves the use of a dew point sensor to provide a signal to the thermostat or the zone valve indicating the measured dew point temperature itself. That dew point temperature is then compared to the chill water supply temperature. If at any point the dew point temperature gets above the supply water temperature, the zone controller will send a signal to the control valve to close down until the dew point temperature drops back below the supply water temperature, and then normal operation of the control valve can begin again. Moving on to the two proactive control strategies. The first one that you see here involves the use of a zone dew point sensor, and this provides a signal again of the space dew point temperature compared to the chill water supply temperature. In this application, instead of shutting down the chill water control valve, we actually are going to open up the primary airflow valve to the space and increase the airflow until the room dew point temperature is suppressed below the supply water temperature. This strategy that you see here would normally be applied on a floor-by-floor or multiple zone per floor basis, and the dew point sensors will be placed in 2 to 4 strategic locations within those zones or within the floor. It's unlikely that the sense dew point temperature would vary by more than a few degrees within those spaces, and it would provide a good estimate throughout the entire space. Zones that have operable windows and doors should always also continue to employ the reactive strategy on top of this, so that in the event that windows or doors are open for an extended period of time, the zone control valve is shut down. This proactive control strategy has the benefit over the other two reactive strategies in the fact that the sudden increase in the primary airflow rate to the zone is going to quickly restore the room dew point temperature, and that zone water flow is restored upon restoration of the zone dew point temperature dropping back below the supplied dew point temperature. And this last proactive strategy that we're going to touch on involves, again, a dew point sensor in the space. Again, this should be located in a couple key points on a floor or in a key point within multiple zones. And with this strategy, what we're trying to do is have a constant offset between the space dew point temperature and the supply water temperature to the space. So as the space dew point temperature increases, you'll see a slight lag, and then the chill water supply temperature is going to be increased, so that you're never supplying water to the space that's below the space dew point temperature. So at no point in time would you ever see condensation with this system. So instead of increasing the primary airflow valve, what we're doing here is that controller for the zone controller, when it detects the increase in space dew point temperature, it modulates a pump to speed up through a mixing valve to do supply water temperature reset, so you're maintaining that offset So this strategy has the benefit over the previous ones shown in the fact that chill water flow to the beam is never interrupted. We're just modulating the temperature up and down versus space dew point until it becomes back in control.